Welcome once again. In previous video, we have studied about common source amplifier with resistive load. While using resistor at load, there are some drawbacks such as fabrication of the resistor with tightly controlled value is difficult. It occupies large chip area and also it consumes large power. So what can be the alternative of a passive resistor? It is that we can use a MOSFET as a small signal resistor if its gate and drain terminals are shorted. It is called diode connected device. Here this transistor is always in saturation because gate and drain have same potential. Look, we know that for saturation this VDS should be greater than VGS minus threshold voltage. So source is common in right hand side and left hand side where drain and gate are at same potential. So we can write VDS greater than equals to VDS minus VTH. So this is obviously VDS is greater than VDS minus VTH. So here you can see that condition of the saturation is always true in this case. Now let's find out the impedance of diode connected device. This is the small signal model of diode connected device. Since gate and drain are shorted, so this V1 is equals to Vx, our equation 1, and this current Ix is given by equation 2, and impedance of this circuit is Vx upon Ix. Here by looking into the circuit, we have 1 upon Gm parallel RO. This is channel length modulation resistance and this is the transconductance of the MOS, and since RO is in mega ohm, so we can write it approximately 1 upon Gm. So here in this circuit we have not taken the substrate bias effect. If we count the substrate bias effect or the body effect, then the 1 upon GMB factor will also comes in the parallel of the this equation 3. So ultimately this output impedance is 1 upon Gm parallel RO parallel 1 upon GMB. So let's solve this equation, and we have Vx upon Ix all in parallel. So we can write 1 upon Gm plus GMB and plus 1 upon RO. I have already told you that this RO is in mega ohm. So this value, whole value 1 upon RO will be negligible in comparison to Gm plus GMB. So we can write it as 1 upon Gm plus GMB. So this is the impedance of diode connected device. Now let's find out the voltage gain of the whole amplifier where the diode connected device is its load. So this is the circuit of common source amplifier with diode connected load. Now we have already found out this the impedance of diode connected device, that is 1 upon Gm2 plus Gmb2, the equation 5, and the voltage gain of the common source amplifier is minus Gm1, and let's write it, the voltage gain is given by minus Gm1. Why M1? Because we are giving input to this M1. So minus Gm1 and the load. So let's write load impedance. So we have find out that this load impedance is 1 upon Gm2 plus Gmb2, this M2 device. So let's take out common from Gm2 plus Gmb2. Eta is the factor, it is given by Gmb2 upon Gm2. So the voltage gain is minus Gm1 Gm2 and this is the factor 1 upon 1 plus eta. Now let's write this transconductance of MOS in terms of the aspect ratio and the bias currents. So we know that the drain current ID1 is equals to ID2, and this factor is also common, both are NMOS devices. So these gets cancelled out and we will left with only the ratio of the aspect ratios. So this is our voltage gain of diode connected load common source amplifier. So this equation reveals an interesting property of diode connected common source amplifier. It is that if variation of eta with output voltage is neglected, then this whole voltage gain of amplifier is independent of bias currents and voltages, which indicates that the input output characteristic of this common source amplifier is relatively linear. So the input output characteristic of diode connected common source amplifier is more linear as shown in this plot. Here if the input voltage is less than the threshold voltage of MOS 1, then output voltage equals VDD minus VTH2. For Vin greater than VTH1, both M1 and M2 are in saturation and ID2 is equals to ID1. So we have this equation. This equation is number 7, and we can see that Vout will follow an approximately straight line. As Vin exceeds Vout plus VTH1, that is beyond this point A, M1 enters into the triode region and the characteristic becomes non-linear. Now let's compare the two versions of common source amplifier that we have studied till now. First of all, the voltage gain of resistor at load is larger than the diode connected load, and here in case of resistive load we have seen that the voltage gain depends on the aspect ratio, the bias current and the voltage across the load, while in case of the diode connected load we have seen that if eta is stable, then voltage gain is affected only by the aspect ratio of the MOSFETs. Linearity is higher in diode connected common source amplifier than its resistive load version. And since we are using resistor at load, so the power dissipation of this common source amplifier is higher than diode connected load. And with the same reason, the area on chip is obviously larger in case of resistive load than diode connected load. Also, we have found that the voltage gain of resistive load is minus GM RO parallel RD, while in diode connected load it is minus GM1 RO parallel 1 upon GM2 for small eta. Here we should write for small eta. And the output resistance of resistive load is RO parallel RD or approximately RD, and the DC load is 1 upon GM2. Diode connected load has lower output impedance in comparison to the resistive load. So this is all about the diode connected load common source amplifier. In the next video we will study about the current source load common source amplifier. So stay tuned and watch the next video also. I hope you like this video, so please share it with your friends and subscribe my channel. Thank you so much and have a nice day.